Hello everyone, here's a video which I said I was going to do and a follow-up to our Diverging mirror lab. This one is going to be a little bit different. We're going to use some math and some geometry. I just thought it'd be fun to kind of prove our Diverging mirror data, or at least compare our Diverging mirror data to some values that we can take and our and the geometry of circles. So just to remind us, in the last video and in the lab that we did on diverging mirrors, we took a ray box. We had these parallel rays coming in. They diverted as they would do on a lens, and we could very simply take a measurement of this focal length. But we also plotted a graph, and we took the slope of this graph and we used some geometry and some calculus basically to get the focal length that way as well. We also looked at the x-intercept, etc. We had a bunch of values which we'll take a look at in a minute. What we're going to do in this video is use geometry to essentially extend almost the circular path of this lens. And we can do that both ways, of course, so there's really going to be two circles. And somewhere in the middle, I'm just going to guess right now, somewhere in the middle is the center of the circle, which would be obviously giving us the radius. So that's going to give us the radius. And what we're going to talk about is the relationship between this radius and the focal length. Now, you might think that it would be just nice and simple. You might think that, oh, look, the focal length is going to be halfway between the center and the center and the edge of the circle. And indeed, it would be if this was a mirror. So if this was just a mirror, if we ignored everything on this side, if we said that the rays did not pass through like they do with refraction, if the rays coming in hit the surface of the mirror and reflected back. So from the surface of the mirror, if they reflected back to the focal point here, in other words, this dotted line was a solid line, an actual ray, then yeah, we could very easily make the statement that this focal length would be half of the radius. So with a mirror, we can say that the radius is 2 times the focal length. However, we're not using a mirror, we're using a lens, and so what we have to consider is the refractive index, because of course, if I had two lenses exactly the same geometry, one of them was made out of flint glass, which has a pretty high refractive index, and the other one was made out of something different, I don't know, plastic, or even diamond, which has an even higher refractive index. Of course, these rays are that's going to affect the angle of these rays, and that then must affect the focal position. So even though the geometry of the lenses would stay the same, the focal position would be different. So we can only use this with a mirror, and so we can't use it here with our lens. The lens is going to be dependent, so the lens focal length doesn't have a relationship, it's not a relationship to the center. This we can't use. We need to consider, so we're going to consider the refractive index, okay? But step one is to look at the geometry of a circle. So we're going to consider these circular extensions, this geometry. We're going to consider a circle, and then we're going to go and say that with that, we can essentially put 2 lines through it. We can put a line through here, which matches with the arc, if you like, this arc shape here. If I was to color it in, let me see if I can do that. This arc in here, right here, I'm going to color that in. It intersects through there. Plus, I'm going to put another line through and just put it straight through the center like this. And so effectively, I'm putting 2 lines through my circle. This is the intersecting chord theory. So that's where we're going to begin. Okay, so intersecting chord theory essentially says you can put any 2 lines through a circle in any way you like. I've just randomly put in this blue line and this red line. And if you then consider triangles made in each section, you're going to have 4 triangles. What intersecting chord theory is based on, there's bunch of principles or assumptions. But the first one to consider is that the triangle A is going to be, in terms of scale, is exactly the same as this triangle over here. Now, obviously the lengths are different, but the size of the angles is exactly the same. So I could make a statement. I could say that this angle here, this angle, is exactly the same as this angle. Okay? And I could also say that, well, hopefully it's clear that this angle, let's call this angle 2, this is the same as this one. And you can do this with any of them. So the key here is that you can produce these equal scaled triangles. So I can prove that just by, it's probably useful just to pull out a couple of these triangles. So let's see if I can do that with my snipping tool. Give me a second. Okay, so I've snipped out my 2B triangles. And what's important to notice here is that when I flip them, let's see if I can do that, flipping it here and there, I think we're good. So looking at it at this point, hopefully you can see here that if I rotate them around, they're actually exactly the same, these triangles, in terms of the angles between them. So we can start making some statements using sine law. So we're going to start doing, we'll say sine of one angle over A is going to be equal to sine of another angle over B, and of course we can keep going with the third angle, sine of C over C. Okay, so before we start making our sine rule assumptions, I'm just going to label some of these corners. So we're going to keep track of this, and we're going to use these all the way through, first of all in our proof of intersecting chord theory, and then when we use chord theory to solve essentially for the radius of the circle. So here we go, we've got P represents this intersecting part here, Q represents this intersecting part, X is where the two chords cross, and then we've got U and V. So first job is to now label the P, Q, U, V's and X's on my two triangles that I cut out from these intersecting chords. Okay, so I've labeled my triangles with the same letters as the intersecting chords. What's important to note is that they both share X, okay? And so we're going to have a shared angle, B, the two B triangles down here. In other words, the angle between the red and the blue chord is going to be the same for both of these. So these angles are going to be the same. Okay, so we can start doing our sine law. So here we go for the first triangle, for UXP triangle. I'm saying that sine theta 1 over the length XP, right here, is equal to sine theta 2 over the length UP, which is equal to sine theta 3 over the length UX. So that's for triangle 1. Let's do it for triangle 2. So it's going to be the same principle. So sine theta 1 over the length XV is equal to sine theta 2 over QV, which is equal to sine theta 3 over QX. And remember, this is all based on the idea that these triangles are equivalent in terms of their angles, not in terms of their lengths, but in terms of their angles. So to always remember that this is where they came from. We have this triangle here and this triangle here. They're different sizes in terms of lengths, but their angles are equivalent. And so I'm able to put these theta 1s being equal to theta 1s, the theta 2s being equal to theta 2s, and the theta 3s and the theta 3s. These angles are the same. And hopefully you can see what we're going to do here. We're going to start combining these together. In other words, I'm going to solve for sine theta 1 for both of the triangles and then combine these together. And by doing that, I should prove to you that the intersecting chord theory is true, and then we can use that intersecting chord theory to solve. Okay, so first of all, I need to decide which lengths I'm interested in. Of course, with sine law, I have 3 lengths in both triangles. So let's just look back at our original intersecting chords. I'm not interested in U to P, am I? Because U to P is not part of my intersecting chord. It's just how I make the triangle. So I'm going to just cancel that out right away. I do not want to be interested in UP, the length UP. So I'm just going to cross that right out. I'm not interested in that. And then on the other triangle, obviously it's going to be QV. I'm not interested in the length QV because that's not part of my intersecting chord. It's not part of this, either the red or the blue chord, right? So I'm going to lose QV on this triangle. Let's go ahead and cancel that out as well. So QV, not interested in that. So now I'm going to solve for sine theta 1 with my first one. So sine theta 1 is equal to sine theta 2 over ux times xp, and then I can go ahead and put sine theta 2 under here. So essentially, I have sine theta 1 over sine theta 2 is equal to xp over ux for my first triangle. Let's go ahead and do the same thing over here. So sine theta 1 over sine theta 2 is going to be equal to xv over qx. And of course, now I can just combine these together. So here's my chord theory, my intersecting chord theory. I have xp over ux is equal to xv over qx, and of course we lose the angles altogether. And now we can make a statement for each of the chords. I can say that xp times qx is equal to xv times ux. And so that's really important because now we can see, if we look at our back at our original intersecting chords, and remember this can be done on any arrangement of these two chords. You can put two chords through a circle in any way you like. You're always going to get these triangles being equal to each other, at which point you can always say that this is true. So what does it mean? It means, let's take a look, that this xp, which is from here, oops, wrong way. It's from here, let's use blue actually. It's from x to p, this length here, multiplied by qx, which is this length here, is equal to xv, which is this length here, multiplied by ux, which is this length here. And that's very significant because what it means is that we can now do this for our circles from our diverging lens. In other words, from this diagram here, we can say that based on this arrangement that we drew from our diverging lens, we can bring in a circle that looks like this, okay? So I can move this out of the way. I can bring in this circle here. Let's make it a bit smaller, and hopefully you can see that these lines can be brought in and we can have two intersecting lines, but now the difference is now I'm putting one through the center of the circle, and this other one represents the chord from the diverging lens. This one's just the principal axis, and that brings in the center of the circle, which means we can solve for the radius. And once we solve for the radius, then we can look at our focal length, and there's a formula that goes with that as well. Okay, so let's go ahead now that we've got our statement about our intersecting chords. We're going to make a statement now to solve for the radius, which of course would be C to Q. Okay, so we can go ahead and state what we're trying to find. We are trying to get this value here. Let's just make this bold. This here is going to be our this is our radius right there. We're trying to find that. Okay, so let's begin by just stating a few terms. I'm going to say that u to x is equal to v to x. Okay, pretty obvious. So I'm saying that from here to here is equal from here to here. Okay. You wouldn't necessarily get this on any intersecting chord situation. The reason we get it here is because we have this central line through the middle. So we know that this must also be the middle if these are at right angles, which they would be on our diagram. Okay, and now what I can do then is say that this is equal to, each one of these is equal to a half UV, okay? And I'm just going to call UV, rather than keeping it in the term UV, just to make it simple, I'm going to call it L. Okay, so just going to put it on here. This value here, let's make it big. This here is L. Okay, let's just put that in here. So there's L. Okay, so this then, so U to X and V to X is going to be half L. Okay, happy with that? Okay, the other thing I'm going to state is the P to X. So this bit in here. The reason I'm going to state that is because that's one of the measurements I'm going to take from my drawing. Okay, when I sketch out my lens, the two things I'm going to measure are the height of the diverging lens and the indent, if you like. So I'm going to call this H. Okay, so I've restated a couple of parts of my diagram, nothing major. We'll come back to that in just a second. Okay, so now I'm just going to restate my chord theory, my intersecting chord theory, but I'm going to state it now in terms of half L. So I'm going to say that half L, which remember is half of that big thick red line over here, it's going to be half of this big thick red line, in other words it's UX, multiplied by, guess what, half L, okay, that is equal to, so this is now equal to half of my intersecting chord theory. It's UX and VX. So it's actually, I've just restated this bit, and now I'm going to restate this bit over here. So I'm going to say half L times half L is equal to XP times QX. And then further to that, I'm going to change out my XP because, hey, look at this. My XP is actually H. So I can say 1/2 L times 1/2 L, let's put these in brackets just to be careful, is equal to, well, XP is actually H. Okay, because I'd made that statement over here. I'd said that this part here, this P to X, is going to be the equivalent of H. So I'm going to bring that in here. I'm just going to restate it. Let's go ahead and put it XP is equal to H. Okay, so I'm going to bring that in there. There's my H. And of course, it's still going to be multiplied by QX. So let's simplify this down a little bit more. Half, I'm going to factor these out. I'm going to factor these. So half times a half is a quarter. So let's put that in. So a quarter, and then LL is L squared. So there's L squared. The half L and the half L ends up being 1L. So that basically becomes 1L times L. So that just kind of disappears. And then I'm going to divide everything by the H to get the QX by itself. So I'm just going to bring that H underneath. So 4H over the with the L squared on the top is equal to QX. Okay, so we're left with a statement here, which we'll come back to. But let's move on and look at the blue part of the line. In other words, the P, X, C, and Q. So what can we say about that? Well, we can say that PQ is equal to PX plus QX. Okay, hopefully you can see there's a bit of a connection here. See how this is going to come up? Okay, so let's keep going. What are we going to say? Well, this is the diameter, isn't it? Remember, we're trying to find the radius, so let's call this out as the diameter. I'll just call it D. The diameter is PX plus QX. Okay, and now we can substitute these in. So P to X is actually h, isn't it? We've already called that out. So just to re-highlight that, p to x is right here, it's h. Okay, so that's there. Plus, put this in brackets, plus the xq, or the qx, which is this statement here. So that's where this comes in. So I'm going to say it's h plus, well, L squared over 4h, right there. Okay, so now we just need to simplify this down. So we're going to say that the diameter of this circle is 4h squared plus L squared over 4h. What have I done there? Well, we're going to assume that this h here is an h over 1. So we're just going to cross multiply. So 4h times h is h squared. And then 1 times L squared is L squared. And then you end up with the 4h on the bottom. So I'm just adding those essentially fractions. If we treated this as a fraction, we would be adding those fractions together. And that's going to give us our diameter, which means we can go ahead and solve for the radius, because of course the radius is going to be d divided by 2. So it's this statement here divided by 2. So I can restate it as 4h squared plus L squared over 8h. Okay, now I need the measurements from my original diagram from our diverging lens lab. So here we have it. This is the hand-drawn tracing of the diverging lens that I used in our original diverging lens lab. And just using a ruler, I've got 6.1 centimeters or 61 millimeters to represent my L. And then this little gap in here I've got as 4 millimeters, and that's my H. So if I plug those into here and here, I get a value for the radius of this circle, or the center of curvature of these diverging lens, is going to be 118.28125 millimeters. Now I've only really used one decimal place here in my measurement, because 4 millimeters is all I got. So really I should be only going down to one decimal place here, one significant digit, but I'll leave it at that for now, just for fun, because we're just trying to prove this based on our lab data from before. Okay, that's the radius. We said at the beginning of the video that if this was a mirror, I've just noticed that I've got the wrong title. It's not a mirror. If this was a mirror, then we could just say that half of the radius is going to be the focal length, but it's not a mirror, it's a lens, and the refractive index is actually, it does play a role of course it plays a role in how much bending the light does, or how much refraction there is on the light. So there's another formula that comes with this. So let's have a look at the other formula. So here's the final formula we're going to need, plus some of the values we've accumulated so far. So let's not get into where this all comes from. Let's just go ahead and trust the formula, because we're running out of time here. But 1 over the focal length is equal to the refractive index minus 1 multiplied by the reciprocal of the one of the radiuses of the circles added to the reciprocal of the other radius of the circle. What do we mean by the radius of the circle? Well, again, if you extend these out, you'll notice that you actually get 2 circles, and so this would be R1 to here, and this would be R2 to here. Obviously with our lens, we're going to have, these are both the same, and this R value came from the radius of curvature that we just did with our intersecting chord theory. The N value, this N value here, that's the refractive index of the glass that the lens is made of, which I'm assuming is flint glass. And then these 2 values here, these were the ones that we had previously calculated and measured in the lab itself. So I just went ahead and just did a straightforward measurement on my diagram to get 9.1. And then I used the slope of my data to determine a value, and I got 9.6. So the question is, how does that compare to the F value here, when we use this intersecting chord theory value. So let's go ahead and solve. All right, so I'm just going to put some numbers in. So 1 over f, obviously we're going to solve for f. N is going to be my refractive index of flint glass, -1. And then I'm going to go ahead and put in my R1, which is 11.8, and my other R1, which is the same. I'm assuming it's the same on both sides. Okay, there we go. Let's simplify this down. We're going to get 1 over f is equal to 0.66 multiplied by 2, 11 over 8. And that's going to give us, if we plug all these numbers in, drum roll, here it is, 8.939 centimeters. Well, that's pretty satisfying because with all the error given in my cumbersome measurements just using a ruler and the ray diagrams from the very beginning that weren't exactly parallel, to get within, to get pretty close, I'm pretty happy with that. So there you have it. Diverging lens lab, followed up by intersecting chord theory using some measurements from the curvature of a lens, just to verify or prove that the lens lab was a reasonable estimate. That's all from me for now. Until next time.